Okay, hi. This is an optional video of just doing a numeric example, okay? So if you already understand what's going on, you don't have to watch this. I thought it would be interesting just to see the two equations we get for G0 and G1, the estimates of gamma 0 and gamma 1 under the least squares criteria. So I drew a little picture. I'm not sure the picture's correct, actually. I didn't plot this on the computer. And here I have my data. And we want to, so if you want, you could think of this as yi. I like to think of it this way because I like to see this error term here and then think that these distances here are normally distributed. So there's EI, and this is normal 0 sigma squared, independent. Okay, so let's try to find G0 and G1. So find LS estimates for the gammas. All right, well, this starts, we need to solve. So we solve the dq d gamma 0 equals dq d gamma 1 equals 0, and call those solutions G0 and G1. All right, well, this from the last lecture, we know this means that we want to solve the following. We want to solve the sum yi after we cleaned it up, right, 1 to 3. And here we have df d gamma 0 evaluated at g, right? Yep, I'm leaving out the parameters here, but I'm evaluating these at g, so everything's going to be in terms of g here, minus the sum 1 to 3. Here we have the function itself, so we have f x g, and now df d gamma 0 evaluated at g. Actually, this is at g because f could have other things besides gamma 0 in. So this is right. So this equal to 0, and then we also have this 1 to 3, same thing, df d gamma 1 evaluated at g minus the sum 1 to 3 fxg df d gamma 1 evaluated at g equal to 0. Okay, so we have to solve this. Two equations, two unknowns, but they're not linear equations, right? Okay, so let's actually do this. So I have to compute the partials here. So this is equivalent to sum 1 to 3 yi. What's the partial of f with respect to gamma 0? Just e to the gamma 1 xi. So I'm just going to put g1 in there, right? So I have yi e to the g1 xi minus sum 1 to 3. And here I have the function, which is g0 e to the g1 xi, because I'm putting g right in. And now I have, again, this partial term here. So I have e to the 2gi xi when it's all said and done. So I have g0 e to the 2g1 xi, okay, equals 0. That's the first one. When I do the second one, it should be pretty similar. 1 to 3. What's the partial with respect to gamma 1? Well, it should be xi g0 e to the g1 xi, right? So we get sum yi g0 xi e to the g1 xi minus 1 to 3. Now I have the whole function. So I get 2g0, so I have g0 squared. I have the whole function, right? G0 squared, and I have e, and I have my xi. And I have 2, again, I have 2, so I have e to the 2g1 xi equals 0. I think you should believe this. So we have to solve these both. they can be simplified, and now I can plug in the data, right? So using the data here, I'll write it here too, so we have it here. So x and y, 0, 1, 2, 6, 3, 1, right? So we put these in now. So let's do it for the top one. So I have x is 0, so that makes this 1, so I just have 6. My next one, I have plus 3, e to the g1. My next one, I have plus 1, e to the 2g1. So e to the 2g1 minus, let's take the g0 out front, and I have, when I put x0 in, I have 1. When I put x1 in, I have plus e to the 2g1. When I put x2 in, I have plus e to the 4g1 equals 0. Okay, if I do the bottom, one thing on the bottom is I can take the one of these g0s out and factor it out because I'm setting equal to 0. So that goes bye-bye. So I get, when I put x0 in, I get 0 here. When I put x1 in, I get 3 e to the g1. When I put x2 in, I have 2 times 1, so I have plus 2 e to the 2g1. And now I have minus, I just have a single g0 now, and I go one at a time. When I put x0 in, I get 0. Put x1 in, I get e to the 4g1. When I put x2 in, I get, let's see, when I put x1 in, I get e to the 2g1. And when I put x2 in, I get e to the 4g1. So plus e to the 2g1. This should be in the other order, but equals 0. Okay, look, you could do a little cancellation here, but what do you see? You have these different powers of g1. You could do some factoring, but still, you can't escape the fact you have these exponential with different powers. Then you'd have a product of exponentials. So not sure that really helps. And then you have this other unknown down here multiplying this. You can use multivariate Newton's method. There's other ways you can do this to solve this. Multivariate Newton's method is the way to do it, I think. But there's actually, we can exploit something here. So that's very, very smart. So this is the topic of the next lecture. And by the way, if all this doesn't interest you and it feels we're drifting away from linear regression, maybe a little, but it is important if you want to be more than just a user of R and you actually want to understand what the software is doing, this is important. And even as a user of R, in the algorithm that R uses to find these, it does ask for user input. It's too complicated, R can't do everything for you. So you have to understand a little bit what you're doing to do it. So that's all for this one. On the next one, we'll continue with how the main algorithm, the Gauss-Newton method for iterative method for finding the estimates. Okay, we need this. Okay.